for a particular type of problem, you're given the potential that corresponds to that problem, and we'll begin our first simple example here at the end. But you know, we still have some general remarks to make. So we'll show, you know, that quite often there are only discrete possible values of the energy that can exist for this equation to be solvable, right? And you know, if we know the E, if we can solve for the E, we can find the wave function U. And if we know U, you know, given our potential does not depend on time, if we know U, we can calculate the psi, right? Well, the probability density is just the square of the amplitude. The psi is an amplitude. There are lots of names for it: wave function, the psi function, the amplitude. Okay, take your pick. All right, but there are certain constraints, certain almost common sense requirements that you need to place on these psi. They're more sort of mathematical in nature. For example, now we're talking physics, right? We're doing mathematical physics. We're using mathematics to model the behavior of physical systems. So in a sense, it's applied mathematics. Now, as we get higher and higher, say PhD 2 level, it's no longer theoretical physics. Theoretical physics has connotations of taking mathematical tools from the mathematicians and applying them to physics. That's the usual, almost unquestioned, almost unconscious definition of theoretical physics. But at the highest levels, the mathematicians have been influenced by the theoretical physicists, so that mathematics has been helped and progress has been made in math by the theoretical physicists. So those theoretical physicists who are strong mathematicians, you know, people like Ed Witten, for example, nowadays they tend to be called mathematical physicists because they're just as much at home in pure mathematics as they are in physics or theoretical physics. So one of my longer term goals is if you keep watching my stuff and you climb with me M1, M2, PhD 1, PhD 2, if you come up all the way with me, you will end up yourselves mathematical physicists, right? You'll be as much at home in pure math as you will be in mathematical physics. Anyway, so these are kind of constraints here of a mathematical nature, right? But that makes sense in a physical context as well. For example, this psi function, you want it to take a single value. You don't want it to have like two values at some point and at the same time. That seems a reasonable assumption to make. So psi as a function of space and time, x and t, if you know the x and t, if that's given, then you want this psi to just have one value. That seems reasonable, right? Because if it has more than one value, well, how do you interpret this? I mean, with Born, you want the square of the psi function to be a probability density. But if this can have more than one value, well, what does the probability density mean? Right? You got conceptual problems there. So this condition that you place, you know, restriction, if you like, that you place on the psi function seems reasonable. Now another one, so there's three of them, A, B, C. Another condition you impose, you put on the psi function or the u, is that it needs to be normalizable. To normalize means if you now remember psi squared is a probability density, right? So to get an actual probability of the particle being in a certain volume, well, you integrate over that volume. So that's your, I don't know, your dV volume, if you like. And here's the range of your volume. Now the value of psi has to be such that when you square it and then integrate it, the answer has to be less or equal to 1. Right? Remember the definition of probability density if you integrate it over all the volume that it can be in, that particle can be in, then the probability that the particle is somewhere in that volume is 1. Right? So if it's in a smaller volume than your total volume, that probability must be less than 1. Okay? So if your psi is such that it gives you a value that's larger, when you integrate you get something larger than 1, well that conflicts with Born's interpretation of psi squared being a probability density. Okay? So psi needs to be normalizable. In other words, the integral of psi squared is less or equal to 1. Right? And another condition is you don't want sudden jerks. You want your psi function to vary smoothly, right? So the function and the first differential. You don't want sudden jerks in gradient, right? So you want both psi and the first differential to be continuous. Okay. Now we will use all of these conditions, pretty much, I think. In every example that we'll do from now on. Okay. Now, interestingly, these three conditions, when you bring them together and start using them, they virtually impose force in certain circumstances. Your E here to be discrete. Right. So you can look upon the solutions to your eigenvalue. Here, so here's your eigenequation. So that the lambda here would be your E here, and E, the allowed energies. So these conditions generate or force your E to be discrete in certain circumstances. Okay, so it's these that are forcing your E to be discrete. There are only certain allowed values, and that's typical of quantum mechanics, right? Energy, for example, is quantized. That's the Niels Bohr, the Bohr idea. An atom can only have certain discrete energy levels. Right? The electrons can only have certain discrete energy levels. Okay, right? Well, because I've run out of board, but we can continue on next session. But here's our first problem. Using all this stuff, solving the time-independent Schrödinger equation, respecting these three conditions, these three constraints. So what I'll do here now is just state the problem. Can't solve it, don't have enough board. But here are the conditions. Now, as you know, this is a concrete case of a general procedure when you're solving a Schrödinger time-independent equation. Is you're given some potential. You're told what your V is, and then you solve your differential equation, your eigen equation. Now in this case, your potential is nothing. Here's your x-axis here. Here's the origin here in the middle of your x-axis, and in this range between minus a and plus a, the potential V here is just nothing. So there's no field or anything in that area. So V is just nothing in that area. Okay, but this here at A and minus A are walls, are impenetrable. You cannot penetrate them. Right? They're just the potential there. The V there is infinite. Right? So there's just no way the particle, the wavicle, can penetrate this region here. So the psi function in this area and this area, so greater than a and less than minus a, the u, if you like, the wave function is just 0. Here it's 0 and here it's 0. Okay. Now the question is, so u is 0 in that region and this region, and the question is, u equals question mark. What is it? What is u? What form does u take in this region here, between minus a and plus a? And to solve that, we need to solve this equation, right? Now, in this region here, v is nothing. In this region here, v is infinite. Therefore, u has to be 0. So what it boils down to, u is nothing here, we know that immediately. So, but here v is naught, so this term here disappears, and we have to solve this equation, this one, in this region, respecting these three conditions. And actually doing that, actually solving the eigenequation in this region here will give us, you'll see, discrete energy levels, like the E's, the energies here for this problem are discrete, right? They're not continuous. Interesting. And we will solve. What form does u take? The wave function u that depends only on the position x. Right? So we will solve for values of e, and we will solve for values or functions u. What form will they take? And well, that's next session.